Hi, I'm Gabriele Berton and I'm going to present the paper Viewpoint Invariant Dense Matching for Visual Geolocalization. Visual geolocalization is the task of recognizing where a given photo was taken. This photo is usually called a query. This is commonly tasked as image retrieval, where given a large gallery of images with GPS coordinates, the goal is to find the most similar match to the query. The problem is approached using global or local features. Here we propose GeoWarp, a method which takes the best of both worlds. At test time, the goal is to first find a number of predictions using a CNN with global features, for example, extracted with a gem pooling or a NetVal layer. Then we aim to re-rank such predictions. In order to do this, given any query prediction pair, we pass them through a warping regression module, which estimates 4 points in each image. These points are used to apply a homographic projection whose aim is to maximize the similarity between the two warped images, as you can see here on the bottom right. Finally, given the warped pair of images, we use a simple CNN encoder to extract dense local features, which we then use to compute a similarity between the pair. Note that dense local features are highly informative, but they are not resistant to viewpoint changes, and that's why we first apply the homography projections. So now the question is, how do we train the warping regression module? Because there is no large-scale dataset with homography labels, we need to do it in a self-supervised way. First, we take an image from the training set. We draw two intersecting trapezoids. We apply a homographic projection on both to extract two images. And now we have two images for which we know the intersection, here shown in green. Given the two images, we can train a CNN that estimates their intersection. Self-supervised training data generated from a single image helps train the network, but it does not represent real-world distributions. This is because query prediction pairs at test time have temporal variations, such as scars or illumination changes, as you can see here on the bottom right. To overcome this issue, we mine query-positive pairs in a weakly supervised manner and use them to better train the network, introducing two losses. The first is a feature-wise loss. Given the pair, we compute the pairwise warping, their dense local features, and minimize the distance between the resulting features, helping the model to increase its robustness. The second is a consistency loss. We apply random augmentations to the pair of images, then estimate the homographies for augmented pairs, and finally use those estimates as pseudo-labels and maximize the similarity among such predictions, similarly to what is done in contrastive learning. Here we show results of a number of baselines with and without GeoWarp on two geolocalization datasets, using threshold distances for positives of 10, 25, and 50 meters. We can see that using GeoWarp constantly improves the results regardless of the backbone and pooling layer. Here are comparisons with other methods. We see that on average, GeoWarp achieves better overall results. The warping coefficient K influences the difficulty of self-supervised training data. Using a higher K results in more difficult training data, which leads to a model that performs stronger transformations. We can see in the plot on the bottom left that using a lower K is beneficial when the distance threshold for positive is lower, such as 10 meters, while results for higher distances benefit from using higher values of K. Here we see some qualitative results. It is clear how warping the images helps them to increase the similarity and simplify the search for correct predictions. Finally, there are more qualitative results of our pairwise warping applied to a query prediction pair and the comparison with previous methods. Thank you for your attention.